Today we are going to talk about Ampere's law. Now, Ampere's law is a relation between the current piercing the plane of cut. Okay, خلاص نبلش من جديد. Today we are going to talk about Ampere's law. Ampere's law is a mathematical relation between the line integral of the magnetic field around some loop and the current piercing the area enclosed by within the plane of that loop. The importance of Ampere's law is that when one has a high degree of symmetry for the current distribution, then Ampere's law can be utilized to calculate the magnetic field in a very simple manner. Actually, as such, Ampere's law can be thought of as the counterpart of the counterpart of Gauss law. You remember in Gauss law, when we had a continuous charge distribution with high degree of symmetry, and we were to find the electric field of this continuous charge distribution, then rather than doing integration by dividing that charge distribution into small parts and then finding the field of each part and then integrating, we utilized Gauss law by selecting a Gaussian surface and then relating the flux through that Gaussian surface to the net charge inside that Gaussian surface. And for high degree of symmetry, we were able to take E outside the integral, the surface integral, and therefore the calculation of the electric field boiled down to a very simple manipulation. Actually, Ampere's law, just keep in mind that it is we can utilize it in a way very similar to what we used in the case of Gauss law to find the current density, because the magnetic field, sorry, for some current distribution. Because what we know, what we have in hand so far for finding the magnetic field of any current distribution is just the Biot-Savart law, which is based on dividing that current into small elements IDS, and then finding the field of each one of these and then integrating. Here, when we use Ampere's law, things will become much simpler, and even we don't need to do integrations. But let's first understand what is Ampere's law, okay? What does it say and how to comprehend it, and then after that we will move to the next step, which is utilizing Ampere's law to calculate the magnetic field of some current distributions when we have high degree of symmetry. So to utilize Ampere's law, or introduce Ampere's law, assume that there is a region in space where I have magnetic field, some magnetic field, you know. These are the magnetic field lines, regardless of the source. Of course, these should be closed circuits, as you know, the magnetic field lines, but I'm just showing part of these, okay? And what Ampere's law, and let there be some currents. Now, this magnetic field is in the plane of the board. So these are the lines of B. Now, and let there be some currents piercing that board normal to it. So, for example, this is just a current, a line, for example, which carries a current I1, and it is into the board. This is I2, it's out of the board. We are familiar, I think, with this convention. When you put this X, it means into the board. This is something coming out of the board, okay? This is I3 here, this is I4 here, and so on. So these are different currents that are piercing the board in or out of it, and they are in this magnetic field, Now, what Ampere's law says is the following. It says, take an arbitrary loop, closed loop, okay? Call it C. So C here is a closed loop. It's a virtual loop. It doesn't need to be a real loop. It might sometimes coincide with a real loop, for example, the borders of a wire or so on. But in general, this is a virtual loop. So it says pick up this loop, okay? And what it says is, and evaluate this integral. take this integral, b dot dl, and you have a circle here, and you have a c. Now, well, we have seen this integral with a circle before when we discussed Gauss' law. But in that case, it was an integral over a surface. But here, it is not over a surface, okay? So it is an integral over this closed loop. And I will explain what does this mean, okay? And so this circle means it's closed. And I put c here to just remind ourselves that this is an integral over a contour or a loop, okay? We call this contour. So this is called contour integral or line integral, okay? Line integral. So it's integrating the magnetic field over this loop. It says that this integral, okay, is equal to mu naught I net, if you like. Now, mu naught, we know what's mu naught. It is the permeability of free space. I'm assuming that the whole setup is in free space. And I net is the net current piercing the plane, the area defined by the loop. So in this case, this red contour or loop, contour, or you can call it loop, contour, whatever you like, this contour encloses an area, which is this area. So I net here is the net current that is piercing this area, okay? So let's first understand what is the left-hand side. What does this mean? Well, it means actually this is B dot dl. Now we know, for example, that this magnetic field at different points on the loop will have different directions. And this is usually, for example, if you want to find the magnetic field here where the magnetic field line is shown explicitly, we know that the magnetic field is always tangent. So at this point, this is your magnetic field, for example. At this point, this is the magnetic field. At this point, this is the magnetic field. At this point, this is the magnetic field. At this point, this is the magnetic field, and so on. Of course, the magnetic field exists at each point in the loop, but because the magnetic field lines are not shown at each point, okay, I'm not showing it. But in principle, I mean, magnetic field exists at each single point on this contour, this loop, and at each point it has a given magnitude and direction. Now assume that I divide this whole contour into elements dl, okay? Each one of them is length dl. So dl1, dl2, dl3, and so on and so forth, okay? So each one of them. Now, because these are small enough, then you can take them as straight line, infinitesimally small, as we always know. Now, the magnetic field, of course, is a variable. It's not, in general, at different points on the contour here, it has different directions and different magnitudes. In general, it can be anything, okay? But within a given dl, let me consider this dl in particular here. So this is my specific dl in this case. Along this dl, it can be taken to be approximately constant. Now, this angle here, theta, is the angle between the direction of the magnetic field and the direction of dl. Now, note when I put a dl here, showing it as a vector, I'm defining a given direction, because this dl could have been chosen in the other way. I mean, why to take dl this way? Why not to take it this way? It's up to you. So if I take this dl this way, then this means this dl is also this way, this dl is in this way, this dl is this way. So what I'm doing in this case, I am choosing a direction to traverse the loop by choosing the direction of the vectors dl. Now, should it be clockwise or counterclockwise? It's completely arbitrary. It's up to you. And the Ampere's law is independent of what choice you make, okay? But once you make a choice, remember that choice, because this is important. So assume that I take it in this case, the dl is in this way. So in this sense, I will be traversing the loop in the clockwise direction. Why is this? Because look, this integral now, what does it mean? It is actually the limit, this integral is the limit of the summation of b dot bi dli when n goes to infinity. You might call this also delta Li, so that's irrelevant. So this is delta L1, delta L2, delta L3, delta L4, delta L5, and so on. So all of these, I divide this into n delta Ls. Each one of them, I give it a label delta L1, delta DL1, DL2, DL3, DL4. And the magnetic field for each DL will be different. For example, for this DL, the magnetic field has this magnitude and this direction, and so on and so forth. Okay. Now, Bi dot DLi, this is the dot product between B and DL. And the dot product, it means what? This is actually Bi DLi cosine theta I, because the dot product between two vectors is the product of their magnitudes multiplied by cosine the angle subtended by these two vectors. So this is a scalar quantity, okay? And this is so this quantity, when you take B at each point, and for DHDL, and construct this product, and then sum these up. These are just scalar quantities, numbers. When you sum them up all together and take the limit as n goes to infinity, then actually you are getting this line integral. So this line integral is the physically you can think of it as the dividing this whole loop into small dLs, taking B on the position of each of these dLs, constructing this scalar product between B and DL, Bi and DLi, the corresponding L, and then summing over all of these, adding up all these components, which are just number scalars, and taking the limit as n goes to infinity. Okay, so this is what you do. Now, so if you take this limit, it goes to infinity, then actually this reduces to an integral, and this is an integral over the whole loop. So we call it contour integral or line integral, and we refer to it by putting circle on the integral sign to indicate that it is over a closed loop, and a C to remind ourselves that this is a loop or a contour, not a surface. Okay, so this is the meaning of the left-hand side. Now, what about the right-hand side? Well, mu naught is mu naught. I net is the sum of all the currents that are piercing the plane defined by the loop or by the contour. So in my case, it is this red line. This is the contour. This is the area defined by this contour. So this is the sum of the currents that are piercing this area. Now, so this includes the sum of I1, I2, I3, but not I4, because I4 is outside this contour, this area, and therefore it doesn't count. Okay. Now, when we want to sum these, we know that some currents are coming out, some currents are coming in. Okay. So we have to define a sign convention taking which one will take it as positive and which one will take it as negative, because they will cancel each other. Okay. Even if they do not cancel, we need to define a positive direction for the flow of current. This is not arbitrary. Now, here comes the importance of the sign of how we choose DL. As I said, when we choose the DLs in this way, then as you go on adding up the DLs, as if you are traversing the contour in carrying out this integral, you are traversing the contour clockwise. Okay? So when you traverse the contour in a given direction, to determine the direction of the positive direction for the current, what you do is you let your right hand fingers curl with the direction that you opted for to carry out the line integral. In this case, it is clockwise. Your thumb in this case will be defining for you the positive direction of the current. So in my case, this is how I am traversing the contour. My thumb is into the board, Therefore, I1 is positive, I3 and I2 are negative in this case. And therefore, I net in this particular example will be I1 minus I2 minus I3. Okay, so my result becomes now is that the line integral of the magnetic field that exists on the contour here, on this contour, which is completely arbitrary. Choose any contour, okay, and calculate this line integral. It's an abstract quantity, I'm aware of that, but calculate this line integral. Then the Ampere's law says that this line integral is equal, okay, so it's a complicated integral, but it's value, it's a number, because the magnetic field at different points is a vector which has different magnitudes and different directions here. And when you calculate this integral, you get a number. This is a definite integral, and we'll get a number. This number that you get after when you calculate this complicated integral, or complicated looking integral, boils down to what? To just mu naught, this constant, multiplied by the sum of the net currents piercing, or the net current piercing the area surrounded by this contour. So you see, so Ampere's law relates this integral to a simple quantity, very easy to calculate actually, which is just sum of currents piercing a given area, which is very easy to know. Okay, so that's what Ampere's law say, and it relates these two quantities. Remember the sign convention, as I mentioned. In this case, I take it this way. Now, what happens? You might ask, what happens if I take the dLs in this direction? In this case, of course, the positive direction of the current will be out. Okay, so I will get minus I1 plus I2 plus I3. So I will have the whole thing on the right side multiplied by a negative sign. Yes, that's true, but when you do this, each dl will be replaced by minus dl. It's opposite. And therefore, the left-hand side will be also multiplied by that minus sign. So the equality remains the same. So it's independent. This relation is independent of what direction you choose to traverse the contour. The important thing is once you choose it, you stick to it and you evaluate it accordingly. Okay? So this is the Ampere's law. And it's evident probably now you started noting the similarity with Gauss' law. Just let's remind ourselves what was Gauss' law. It was saying that if you have a Gaussian surface in an electric field, then what was this, the Gauss' law, what was saying? It was saying that this integral, but now over a closed surface. This is a Gaussian surface. Take any closed surface. This integral, which had a physical meaning in that, in this sense, which is the flux of the electric field through this surface, okay, was equal to what? Was equal to Q enclosed divided by epsilon. So again, a complicated integral over a virtual surface, okay, was related to a very simple quantity, which is how much charge you have inside that surface. So Ampere's law, in this sense, is similar. At least, you know, it has resemblance. It's not similar because the integral is different and there's no flux. This is not a flux of a magnetic field or anything. But, you know, it resembles, the idea resembles what we had in the case of Gauss' law. Of course, what remains now is to see how we can utilize Ampere's law to calculate the magnetic field when we have high degree of symmetry. By now, I think, and from your experience with Gauss' law, I think you would have guessed what would the approach be. The approach would be simply, as in the case of Gauss' law, is not to integrate. So with this integral, if you find some c, because this is valid for any c, for any contour, okay? It's independent of anything, and its value depends only on what is you have inside, the currents that are inside it, okay? There is a couple of checkpoints that will be popping up soon, so that we make sure that you understand these points. So the idea in utilizing behind or utilizing this Ampere's law to calculate the magnetic field is that if it happens that you know that there is a symmetry of the current that is generating that magnetic field, okay, in a way that when you choose a specific contour, so that at that contour you can take B outside the integral. B will be uniform, B will be parallel to DL, and so on, so that you can take it outside. So it becomes, this reduces to be a sum over the DL. What is sum over the DL? It is the circumference of the contour. And so this will be equal to mu naught I net. I call it I net, okay? Now, this is very easy to calculate. Let's just find the circumference. And so B will be mu I net divided by this DL over the contour. Okay? So count now what is the net current piercing that contour, the area enclosed by that contour. Okay? Put it here and then divide by the circumference. You get the field at the contour, the field at the contour, which is where you want to find the field, for example. Okay? So the idea and the strategy for applying Ampere's law to find the magnetic field is as simple as this. And as you can see, it's quite close to the same strategy, to the strategy that we apply when we utilized Gauss' law to find the electric field of charge distributions that have a high degree of symmetry. Now, I will apply this to finding the magnetic field for some current distributions where I have this symmetry.